Okay, so in this video, we are going to talk about different polygons and some of the angles and sides and relationships among those angles and sides. So here what we have is a nice little chart that has some pictures, and then as the polygons get a little bit more intricate, we're not going to show those pictures and we're just going to learn from those patterns. But I want to first draw your attention to interior angle sum right here. So it says that this sum of degrees in any polygon can be determined by the number of triangles that can be drawn within the polygon. Complete the table below, and we're going to look for patterns of the sum to the degrees of any polygon. So what they're showing us here is that a triangle is a triangle. It has three sides and it has one triangle within it. And we all already know that triangles have 180 degrees. So then they're giving us a quadrilateral, which is any four-sided figure. It doesn't have to be a rectangle or a square, but anything with four sides. And that if we start drawing in some of these diagonals, we're going to see that we have, even though we have four sides, we have two triangles. So if we have two triangles, we have two sets of 180 degrees. So we're going to have 360 degrees because that's 180 plus 180. The next shape that we have here is a pentagon, which has five sides. And if I take any vertex, they just happen to choose this one in kind of the upper left-hand corner, and go to the other vertices, we're going to get 1, 2, 3 different triangles. So how I got 540 degrees was by multiplying that 180 degrees by 3. And we're going to keep going. Next, we have a hexagon, which has 6 sides. When I count how many triangles I can draw within that hexagon, there is 4. So I'm going to do 4 times my 180, because there's 180 in each of these triangles degrees. We get 720 degrees. And now we have to start looking at our patterns here, right? Because I'm not going to draw a heptagon. I want to figure out, well, how many sides a heptagon? This is also sometimes called a septagon. So I do want you to know both of those names for a 7-sided polygon. Notice here what's happening. When I go down this column, obviously I'm just going to be adding 1 each time. For the number of sides, hepta is a prefix that stands for 7, so there's going to be 7 sides. But then let's look at this column here. 1, 2, 3, 4. So I'm going to assume then that there are 5, since I'm following a pattern. It's a definitive assumption based on mathematical fact and pattern, that there would be 5 triangles within there. So if I did 5 times 180, I'm going to get 900 degrees. Octagon, we all know that's our stop sign, right? That prefix stands for an 8-sided figure, and that is going to have 6 triangles within it. If you don't believe me, go ahead and draw one. So when I do 6 times 180, I get 1080 degrees. My nonagon is a 9-sided figure. That showing here, just to keep you on track, would be 7 triangles that we can draw. 7 times 180 gives me 1260 degrees. My decagon is a 10-sided figure. Deca means 10. Think about decimal places, and the decimal system is all increments of 10. That's going to have 8 different triangles in it. Again, don't believe me, pull up a picture of one. And so when I multiply that by 180, I get 1440 degrees. So this chart kind of outlines, again, what the polygon would be, the number of sides it's going to have, and the number of triangles. And if we know the number of triangles, we can know the sum of the interior angles. And this column, that's really our goal here. This is what we were trying to find, because this is going to help us solve so many different kind of geometry problems here. So of course, now if I wanted you to find a dodecagon, which is a 12-sided figure, without finding that 11-sided figure first, our pattern might have some breaks in it. Or what if I wanted you to find a 50-sided figure? We don't want to keep drawing this column out. So we can use a formula to summarize the patterns that we saw here. So now let's look at this relationship here between the number of sides and the number of triangles. And what you should notice here, if you look at this pattern for a few seconds, is that this is always 2 less, right? We're like subtracting 2 each time. So the sum of the interior angles of a triangle is equal to that number of sides. We've talked about how in math n always means the number of something. So number of sides minus 2, that's going to get us our number of triangles. And then what did we do from here to here? We multiplied by 180. And so that is our formula for the sum of the interior angles so that we don't have to do that whole chart. And that goes for any quadrilateral, like I said, or any polygon. So remember with the quadrilateral, we came up here and I said, oh, it could be, any quadrilateral. It could look really funky. It could look like this, or maybe it looks like this. Anything with 4 sides. When it is a square, which has 4 equal sides and 4 equal angles, that is what we call a regular polygon. Regular means that all of the sides and all of the angles are the same. It's perfect. That's your stop sign. That's your equilateral triangle or that perfect pentagon shape. So we have an additional formula that only applies to regular shapes. A regular polygon is one in which all sides are equal. Therefore, all angles are equal. So to find the measure of an interior angle in a regular polygon, what we can do, we can do our S value, which is coming right from up here, and we can divide it by N. What that means, coming back up here, if we were going to do S over N and make another column, what do we know about the angles of an equilateral triangle? They're all 60 degrees. I did 180 divided by, and I'm going to put an N here, so we all know that N is going to be our number of sides, divided by 60. What do we know about a square? All of those angles are 90 degrees because we took 360 and we're dividing it by 4. So if I wanted to know what one angle of my pentagon, my perfect pentagon, was going to be, I would take 540 and I would divide it by 5, and I would get my 108 degrees. And I can do this the whole way down. Again, if this was a perfect hexagon, meaning all of these sides were the same, and then all of their angles were the same, if I wanted to know the measure of one angle, because right now all I know is that all of the angles add up to 720, if I wanted to know what one of those angles were, I would do 720 divided by 6 and get 120 degrees. So there's a couple things we can do here. One is we can find the measure of all of the angles, the sum of the interior angles, right? Or we can find one angle as long as it's a regular, as in perfect polygon. So on the back here, for interior angles practice, I'm just going to show you a lot of the things that you can do. I'll do the odds, and then I will leave the evens up to you to try. So the first question I'm getting here is that the sum of the interior angles of a 15-gon. A 15-gon just means that it's a 15-sided polygon. So we had a formula for this, right? We said that S is equal to n minus 2 times 180. That's going to be 15 minus 2 times 180. So S is going to be equal to 180 times 13. And I'm going to let you put that in your calculator. And we should get 2,340 degrees for our answer. Okay. What is the measure of each interior angle of a regular pentagon? So to do that, we need to find the total. We can do that using our formula, or we can come back up here to our chart and say, oh, well, pentagon was 540. We've actually done this problem already. We want to say that S is equal to 540 degrees because we did it already. I'm not going to make you do that twice. And then we know that we're going to do S divided by N. So we're going to divide that by, it's a pentagon, so divide that by 5, and we're going to get 108 degrees. So those are the two formulas and how you would use them. You'll do a similar process here for 2 and 4. And so that has to do with all the inside angles, but we had exterior angle theorem before, that we were able to use one outside angle and two inside angles, the two remote inside angles, to find that third angle. But this is going to be different. This is our exterior angle sum. So exterior angles are always supplementary to their adjacent interior angle. On the polygons below, find the measure of each exterior angle along with the sum of them. So exterior angles, again, are always supplementary. So if this is 40, this one's going to be 140. If this one's 79, this one must be 101. And if this is 61, remember this is a linear pair, then this has to be 119. So they want us to find the sum of all these numbers. I'm going to add 101 to 119 to 140, and I happen to get 360 degrees. Let's try this again. This one I had done for you. I found this 104, 56, 109, 91, came out to 360 degrees. Let's try our pentagon here. Here's a linear pair. This is going to give me 82. If this is 121, this is going to give me 59. If this is 87, this will be 93, 130, and 50, 104, and 76. I want the sum. Sum means add, so I'm going to add all of those values together, and I'm going to get 360 degrees. So I'm going to give you one guess to figure out what the sum of each of these angles would be on our hexagon. What are all of our exterior angles? Notice that when we're doing these exterior angles, they're all going the same direction, these arrows. So what do you think? Yeah, exactly. 360 degrees. So we can make a conclusion. We can make a conclusion that the sum of the exterior angles of any polygon is equal to 360 degrees. So that's a really nice and easy formula, or just a fact to remember, because you don't have to do any specific math to a triangle, a quadrilateral, a pentagon, hexagon, dodecagon, 15 gon, 93 gon. They're just always going to add up to 360, because as the angles on the inside get bigger, those angles on the outside get smaller. If I can, I'll post a video that shows you how if you kind of collapse these spirals, you'd get a circle. We know that a circle is 360 degrees. So let's just do some practice. Again, I'm just going to do 5 and 7 with you. So number 5 is saying, what is the measure of the exterior angle of a regular hexagon? So this is regular of a regular hexagon. So we'll know that our hexagon here, that the exterior angles all add up to 360 degrees, but we want to know what just this one is. So if we just want to know what the one is, well, there's 6 of them. If it's regular, then they're all the same size, so I'm just going to divide, and I'm going to get 60 degrees. Just kind of reverse the problem here. If the exterior angle of a regular polygon is 12 degrees, how many sides does it have? So what this is saying is we have this shape, and we have no idea how many, I drew it like that on purpose, how many sides it has. All we know is that when you extend one side, this is 12 degrees, is the exterior angle. So really, we have this total. We divided it by something. We don't know n because we don't know the number of sides that it has, but we know that it comes out to 12. So we can manipulate this data to solve for n. I can multiply both sides by n, and I get 360 equals 12n, and I can divide by 12, and I'm going to get that n is equal to 30. So this must be a 30gon, as it has 30 sides. All right, I'm going to zoom out, make sure that you have all of this information copied down, and I'm going to have you guys try 2, 4, 6, and 8 on your own, and then we will go over this as a class.